Hello to everyone, and in today's video we are going to be looking at the second order differential equation and how we can solve and get the complementary solution. So generally a second order differential equation is given of this form, and we first of all know that it's a second order differential equation because the highest power of the derivative is 2. So from here this will guide us that it's a second order. Now secondly, to solve this, to get a general formula relating or expressing the second order differential equation, we are going to use the substitution y. So we are just going to call this our equation star. We'll call this our equation star, and then we call this our equation 1. Now this is our equation star. If we look for the first derivative of our equation 1, then we are going to have na e to the power nx. So we're going to call this our equation 2. And if we do the same thing, if we look for the second derivative, the d squared y all over dx squared of this function, then we're going to have n squared a e to the power nx. So we're going to call this equation 3. Now looking at this, if we take our equation 1, 2, and our equation 3 and our equation 3 and put in equation star, then we're definitely going to get a, what's our d squared y on the x squared should be n squared a e to the power nx plus b dy dx is na e to the power nx plus cy should be c, and our y should be a, e to the power nx. So this is equal to 0. So we see here that a is common and e to the power nx is common. So if we factor that out, a e to the power nx, then we're going to have an squared plus bn plus c. Now this should be equal to 0. So directly we have that either a e to the power nx is equal to 0, or a n squared plus bn plus c is equal to 0. So when we look at this, we see that this is not possible because no matter the value of n or x, this function will never be equal to 0. So this is not possible, or we have this. So here, this we have a quadratic, and we know that there are 3 characteristics or solutions of this quadratic. So normally this is called the characteristic equation of the second order differential equation, and the solution of this characteristic equation will depend on the roots of these characteristic equations. So now we're going to go on to looking at the type of roots. So after solving an squared plus bn plus c equal to 0, if we have our roots n1 and n2, and we discover that this quadratic equation has real and distinct root, 2 real and distinct roots. Therefore, the complementary solution will be given as a e to the n1x plus b e to the n2x. Now, if we solve this and we see that it is our characteristic equation is having 2 equal roots, and we name it to be n, then our complementary solution in that case will simply be a plus bx e to the nx e to the nx. And finally, if we have complex roots, if we have complex roots in the form n1 plus or minus I n2, then our complementary solution simply be equals to e to the n1x into a cos n2x plus 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 b sine n2x. So those are the three cases in which we are going to be dealing with. We either have two real and distinct roots, two equal or two complex roots, and for each of these cases they're going to have the particular complementary solutions. So whenever a differential equation is given, you look for the characteristic equation. After looking for the characteristic equation, you look at the type of root. From the type of root, you know the complementary solution of that differential equation. So let's get to examples. Okay, now so this is our first example. Whenever a second order differential equation is given to us in this form, we first of all need to look for our characteristic equation. So normally, if it's usually of the form, whenever we see the second derivative, then this will simply be 2n squared minus n minus 3. So we might want to look at it as letting our dy all over dx to be equals to n, so that the second derivative will simply be n squared, and all that to the power 0 is kind of 1. That is why we have 3 here. So that is just a way for you to maybe understand it, how to get the characteristic equation. So after getting this characteristic equation, we might want to use either the formula method, the completing square method, the try and error method, the factorization method. So whatever method you can think of using, or which is best for you, you can use it at this level to get your the roots of this quadratic equation. So if we try to look at the factorization method, we see that we're looking for factors of 6 such that when we add them, it should give us -1, and when we multiply, it should give us -6. So if we take -3 and 2, we notice that if we add this, we're going to have -1, and when we multiply, we're going to have -6. So we're definitely going to have 2n squared plus 2n minus 3n minus 3 equal to 0. So we're going to factor out 2n into n plus 1 minus 3 into n plus 1 equal to 0. So definitely we'll factor out n plus 1, so we'll be left with n plus 1 equal to 0. So when we look at this clearly, we see that our n1 should be equal to 3 all over 2, and our n2 comma, and our n2 should be minus 1. So here we have two real, the roots are real, and they are distinct. Therefore our complementary solution, y complementary, will simply be equal to a e to the 3 all over 2x plus b e to the minus x. So that's our solution for question 1. Now looking at the second example, to get our characteristic equation, please actually this is voila. Okay, now to get our characteristic equation, we're going to have n squared plus 3n minus 3 equal to 0. So we have this. Now what are the roots? We're looking for factors of so if we have -3, and we're looking for factors of -3, or let's say 3 factors of 3. such that when we add them it should give us 3, and when we multiply it should give us 3. It should give us 3, and when we multiply it should give us minus 3. So basically here we're going to use our formula method. Now to use the formula method, we simply have our n to be equal to minus b minus 3 plus or minus the square root of b squared 9 minus 4 into our a should be 1 and our c should be minus 3 divided by 2a2. So we see here clearly that we have minus 3 plus or minus the square root of 9 plus 12 divided by 2. So our n will finally be minus 3 plus or minus the square root of, now if we remove 1 from there and add, it becomes 10, so it should be 21 divided by 2. So we might want to look at this as to get our roots, we're going to have our n1 will simply be equal to minus 3 plus the square root of 21 divided by 2, and our n2 should be equal to minus 3 minus the square root of 21 divided by 2. So that's what we have. Now, since these are two real roots, they are real and they are distinct, then our y complementary will simply be equal to a e to the power minus 3 plus root 21 divided by 2 plus b e to the minus 3 minus root 21 divided by 2. So generally that's our complementary solution. Now we're going to go to the third example. Now for the third example, we have this. So our characteristic equation will simply be 3n squared minus 4n minus 4 equal to 0. So in this case, we're looking for factors of 12, that when we add that, so if we take 6 and 2, we see that when we add this, negative 6 and 2, we're going to have negative 4, and when we multiply that, we're going to have negative 2. So we'll definitely have 3n squared minus 6n plus 2n minus 4 equal to 0. So basically we're going to factor out 3n into n minus when we factor out 3n, we'll be left with 2 there. So if we factor out 2 here, we'll be left with n minus 2. So if we factor out n minus 2, we're going to have n minus 2 into 3n plus 2. So basically this will be equal to 0. Therefore our n1 will simply be 2, and our n2 will simply be minus 2 all over 3. So looking at this again, we have two real and distinct roots. Therefore our complementary solution will simply be a e to the 2x plus b e to the minus 2/3 x. So that's our solution. Now I'm going to the fourth example. We see that our characteristic equation will simply be n squared plus 6n plus 9 equal to 0. So in this case, we're looking for factors of 9 such that when we add that, it should give us 6. So if we look for factors of 9, let's say 3 and 3, then we see that when we add that, it gives us 6, and when we multiply, it gives us 9. Therefore we have n plus 3 all that squared equal to 0. So we see that this is these are repeated root because it's n plus 3 times n plus 3, which gives us n plus 3 all that squared. So we see that our n1 is equal to n2, which is equal to n, which is equal to let me wipe that. Which is equal to n, which is equal to minus 3. Therefore our complementary solution will simply be equal to a plus bx plus bx e to the minus 3x. So basically that is what we have for this. And now looking at the fifth example, now this is our fifth example. Therefore, to get our characteristic equation, we're going to have n squared minus 2n plus 3 equal to 0. So we see clearly that we're looking for factors of 3 such that when we add that, it should give us minus 2. So basically there are no factors of 3 that when we add, if we take negative 3 and 1, when we add that, it should give us minus 3, minus 2, but when we multiply, it can never give us 3. So if you are really confused when faced with such equations, you can look for, you can use the determinant, the discriminant. So for the discriminant, we know the discriminant is b squared minus 4ac. So b squared minus 4ac. Our b squared here should be 4 minus 4 into a times 3. So see clearly that is 4 minus 12. So basically this is negative 8. Once it's negative, therefore we have complex roots, and if it shows that it's having complex roots, therefore there are no real solutions. We can only use the formula method or the completing square method to get our solutions. So using the formula method to get our roots, and then we use the complementary solution describing the complex roots, we're going to have our n will be equal to minus b2 plus or minus the square root of b squared 4 minus 4ac, so minus 12 all over 2a. So our n will simply be equal to 2 plus or minus, now 4 minus 12 will give us minus 8, and 8 is the same as 2 root 2, so we have 2 root 2 I. Now the I, because we know that the square root, basically the square root of negative 1 is equal to I. That's the definition for a complex number. And no, the definition for the square root of a negative number. For the definition of a complex number is a plus bi. So we have that. So if we continue, we're going to have 1 plus or minus root 2 I. So we see here clearly that our n1 is 1 and our n2 is root 2. So here our complementary solution will simply be equals to e to the n1x. So e to the n1 here will be x into a cos, oh my, a cos root 2x plus b sine of root 2x. So that is our complementary solution. So guys, that's all for the part 4 of this video series. If you haven't checked out part 1, 2 and 3, just do that. I will put a link in the description box and also above the video so that you can have access to that easily. See you guys in the next video.